afternoon, everyone, and welcome to another Australian Water Association webinar. If you have any technical issues or audio or visual issues, you'll find in the text box that there is a number to dial, 1-800-733-416. Also let you know that this is a Q&A session, so at the end of the session you'll be able to ask Troy any questions you might have. Just type it across in the text box at the bottom left-hand side of the screen. And just introducing our speaker, on behalf of the Australian Water Association, I would like to thank you all for joining us today for our Direct and Indirect Potable Reuse Seminar, A United States Perspective. Our presenter is Troy Walker from the United States. Troy is the Water Reuse Practice Leader and Membrane Treatment Service Group Leader for Heisen and Sawyer, a leading environmental and consulting firm based in the United States. Thank you and welcome, Troy.
Thanks a lot, Kerry, and good afternoon, everybody. Good evening from me. You would have heard already by now that I'm from the United States, but not originally. I'm one of you, and I'm an expat. I've been living here for nearly 5 years now, working in the water industry, specifically on reuse and on membrane treatment systems. And what I'm hoping to do today is to give you a bit of an overview of what's happening in potable reuse, both direct and indirect, in the US. And just make sure I'm doing this the right way. There we go. I'm going to do a bit of an introduction, talk some about the drivers for reuse, and then I'll walk you through some of the different states across the country here, because there are quite some significant differences and some significant differences in the drivers for reuse across different parts of the country. It's something that's important to give context to. One of the big things that is important to talk about with the US, I think, straight away, and this is something that when you come from Australia that is immediately apparent to you, is that it's a really big place. While the land surface area of our two countries is quite similar, the US has a lot more people than Australia does, and it's split across a lot more jurisdictions. And that difference in jurisdictions, I think, makes quite a difference for us in the water treatment world and in the potable reuse world, because of the different regulations that will apply. Water is regulated on a state basis. The Environmental Protection Agency does provide a set of rules for drinking water quality that is mandated, but when it comes to the permitting of reuse projects, that happens at the state level. And so we need to deal with a lot of different states. Now, some of those states can be quite large, and as I'll show you as we walk through, some of the states that focus a lot on potable reuse have populations in and of themselves larger than Australia to start with. So jurisdiction is a big issue. In the United States, there is a fair degree of movement going on in population. There is a lot of population that is growing on the coasts and towards the arid areas. The Midwest, for economic reasons, is effectively starting to empty out, and a lot of people are moving to areas in the southeast, places like Florida and Georgia, the Carolinas, and they're moving west to places like Arizona, where I'm sitting right now. Places like California and Nevada are getting increased populations, and a lot of those areas at the same time are water stressed. And despite what you might hear from the federal government here sometimes, climate change is impacting the United States, and there has been an increase in uncertainty with water supply planning because of extreme weather events. And the graph you can see there is the number of different types of events that have been occurring, and an increase in frequency of those events. That impacts water quality and impacts water availability in a number of different ways, and in particular, I'm going to talk about drought, which, like Australia, has been a particular issue here, particularly in the western states, but other climate impacts as well that are impacting water supplies and acting as drivers for water reuse. And water reuse is happening in the US. 80% of the water reuse happens in 4 of the states: Florida, Texas, Arizona, where I am right now, and in California. And interestingly enough, Florida is the biggest state for reuse in the country. There is reuse in other parts of the country, and I'm going to talk a little bit about that as well, but those 4 states, and I'll explain the reasons for that as we go on, have the bulk of water reuse. And a lot of it is based on climate, and there are different set of climatic conditions for the US across the country and different storage conditions. In the West, it's about drought and it's about water availability. It's a typically dry environment. The West, including the coastal California, Arizona, New Mexico, Nevada, they are desert or desert-like areas with very low snowfall. And we rely here on snowpack on the Rocky Mountains for water supply and snowpack on other mountain areas. With climate change, that snowpack is often decreasing, and so that puts a significant pressure on water supplies. In the southeast, in Florida particularly, the storage is an issue, and the storage can't keep pace with population growth. In the northeast, they get plenty of rain. Similarly, they have limitations on storage and groundwater, and I'm going to talk to some examples of that a little bit later on. So from a drinking water perspective and from drinking water drivers for reuse in the US, a lot of it is about drought and a lot of it is about water availability. But also it can be about the deferral of potable water infrastructure. If we have effective potable reuse systems, that may avoid the need for additional drinking water plants or for increasing the size of those water plants. Seawater intrusion is an issue, particularly on the west coast and in Florida, where groundwater is used. And we have, as I mentioned before, population and lack of storage. But also, not only from a drinking water perspective, but also from a wastewater perspective, we're seeing potable reuse being driven. And this is something that we're seeing on the East Coast, particularly in Florida, but also some of the other states in that area, that nutrient loads to the water supply, for environmental discharge, and nutrient loads, particularly into the coral reefs off of Florida, are being significantly reduced. And so with those low concentrations of nutrients that need to be achieved, there is a real advantage in starting to look at reuse, because by reusing some of that water, the load can remain the same, but the concentration of the effluent can go up because there's less volume going out to discharge. And so there's quite a big drivers in places like Miami, in places like Tampa in Florida, for nutrient reduction being a real driver for reuse and potable reuse, as opposed to necessarily a water need. So the map you can see on the right hand side there gives a bit of a picture at a glance of the state of regulation for potable reuse, both indirect and direct. Where you see green states, that means that there's no regulations for reuse at all. The purple states have some regulation for reuse, but it's non-potable. Where you see the light blue, they are states where indirect potable reuse is permitted or has been permitted, and the states that are brown are those that have seen direct potable reuse permitted. And you'll see that there's 2 states. North Carolina has it on the books, but hasn't done it. Texas has permitted 2 direct potable reuse systems, and I'm going to talk a little bit about those as the talk progresses. Where there are hashed lines, you can see, I think, Georgia, Florida, California in particular, that's where regulations are pending for direct potable reuse, or work is being done towards regulations for direct potable reuse. And I'm going to talk a little bit about that, particularly the California example, which my company and a number of others in the field have been heavily involved in. But first, some definitions, because it's important when we talk about potable reuse and indirect potable reuse and direct potable reuse, what are we talking about? Because the definition really hasn't been all that clear. When we're talking about indirect potable reuse, we're talking about taking wastewater from urban municipal wastewater, treating it through a wastewater treatment plant with settling biological processes, and then that is then further processed by some kind of advanced treatment. Now, don't be put off by the fact that I have a picture of reverse osmosis there. It doesn't necessarily have to be that process, but there are advanced treatment processes that minimize the risk of pathogens, remove chemical risk as well, and then produce a water that is sent in some way to the environment. There's an environmental buffer either in a reservoir or by reinjection into groundwater. And that's a definition of an indirect. Now, California recently has started to change some of the terminology, and I think in a helpful way. Rather than talking about direct and indirect potable reuse, they talk about where the water is going and what it's being used for. So rather than saying indirect potable reuse for surface water, that's now termed surface water augmentation. Similarly, if we talk about water being applied to a groundwater or being reinjected into an aquifer, that's called groundwater augmentation. Now, where that becomes quite useful is when we start to talk about direct potable reuse. And the difference between indirect and direct is that we take away that environmental buffer. There's no large reservoir, there's no groundwater storage anymore. Instead, after treatment by an advanced treatment process, there's some engineered storage. And we say engineered simply because it's a storage that's big enough for our controls and our operations to be able to respond to an issue before that water gets back into the drinking water supply. But a much smaller volume than we would see for an indirect system. Now, California again has renamed some of these because one of the challenges with defining direct potable reuse, I should say, is that it was given to two things. It was given the definition to water that was then taken to the head of a water treatment plant, or water that was taken directly into the distribution system from advanced treatment. So rather than get tangled up on that different definition, California has referred to this now as raw water augmentation and finished water augmentation. And those of you that are paying close attention will realize I've mixed those two up. The raw water augmentation should in fact be feeding into the drinking water plant. Finished water augmentation should be feeding into the distribution system. There's a prize for any other mistakes that you see in the slides as we go. There is a long history of potable reuse in the United States, and I've got a list here of projects both within and without the United States, and I've just kind of highlighted the ones that are here in the United States. Starting in the 1960s, there were in fact potable reuse systems prior to that in the 1950s for emergency use. But engineered systems started to be included in the 1960s. A system in Montebello Forebay in LA, which I'll talk a little bit about. But you can see, without delving into each one of those projects, right through from the 1970s to the early 2000s, there has been potable reuse in the US for some period of time. Substantial growth in that reuse throughout the 2000s, particularly during the drought period, which kind of followed on the back of the Australian drought. So when Australia came out of drought, the US was jumping into one. So a lot of development in that period. And then, as you can see, a couple of important projects more recently in 2013 and 2014 in Texas, which were direct potable reuse systems. I'll talk some about those as well. And the elephant in the room when we talk about potable reuse, of course, in any country, particularly in Australia and also the United States, is that of the de facto reuse. There's lots of cities and towns of quite some size in the United States that live downstream of some of the major waterways, and so there's becoming an increasing acknowledgement that de facto reuse has been occurring for some time in the country already. And an interesting graph here that sort of shows a number of cities that were looked at in this particular study that showed that 10 of them had 100% de facto reuse in low flow conditions. And so de facto reuse is something that is occurring and being acknowledged here in the US. And what's important is that planned potable reuse in some ways provides a better management of some of the potential risks from these systems because we are engineering a system to manage it. So now I'm going to spend a bit of time talking about California, which is the state that gets a lot of attention for potable reuse in the United States. for a number of good reasons. It's done it a long time. It has been quite an innovator over the years in a lot of technologies and the adoption of those technologies. And in many ways, it does drive some of the trends in the country and some of the regulatory approaches in the country. The real driver for reuse in California is where the next drop of water is going to come from. As I mentioned before, California is a very dry state, particularly the southern half of the state, and really anything east of the coastal range is a very arid environment. Between about 2008, 2009 through to 2016, California saw the worst drought that it has seen on record. Sounds familiar, doesn't it? But California was seeing a lot of the issues that Australia had been seeing in the decade prior. And that drought has, in the last year, been reprieved, but in the long term, California generally is a very dry climate. Southern California in particular is worth talking about. That's, if we bundle Greater Los Angeles, Orange County, San Diego together, that yellow area that you can see on the bottom of the graph there, that has a population roughly the same size as Australia. And it has a very low rainfall. It is effectively a desert. If you look at the little graph there on the bottom left, the data is annual rainfall data for the city of Los Angeles taken from about the 1880s to current, and the yellow line through it is the average of that data. Above that, just for interest's sake, I put the average rainfall for Perth, which is the grey line, and the average rainfall for Sydney, which is the blue line. You can see Los Angeles is a pretty dry place and really doesn't have sufficient water in order to support it. And so a lot of water from California has to come from different sources. One of those is groundwater, and in fact the original source of water was groundwater for the areas in California, but that's come with its own issues. One of those has been land subsidence, and I love that photo on the right hand side. You can see there is taken from San Joaquin Valley, which is north and central California. Now the issue here was over-extraction of groundwater from irrigation, but those markers you can see are actually the ground level at different times in history, and the impact that water over-extraction has had on the ground level. It's almost hard to believe from that photograph, but that's ground subsidence. In the coastal regions around Los Angeles and Orange County, seawater intrusion into over-extracted aquifers is an issue. Orange County is called Orange County because it used to be a lot of oranges grown there. It was an agricultural area. And it was a successful agricultural area because of groundwater extraction. And over-extraction of that groundwater has led to seawater intrusion, and a lot of reuse in that area has initially been dedicated to managing that seawater intrusion. One of the other things that we're seeing in California at the moment as well is that in that search for the next available drop, a lot of groundwater that had been kind of left alone because it was difficult to treat is now being tapped into, and more complex treatment techniques and processes are being used in order to access that more challenging water. As an example, in the Palm Springs area, which is about an hour and a half to the east of Los Angeles in the desert, chromium-6 is a naturally occurring problem in the water supplies there, as is things like arsenic and other heavy metals that are a concern. In the Los Angeles basin, the post-war years have seen a lot of industrial contaminants leach into the groundwater, and a lot of those water supplies now, with things like TCE, TCPP, are being treated in order to access that available water supply. But the groundwater is not enough, and so Southern California relies on imported water supplies, and significant imported water supplies. Historically, that started for Los Angeles in the 1910s and the 1920s, where Owens Valley, which is about 200 miles from Los Angeles, a number of canals were built to drain water from that area. The engineer on that project was a gentleman by the name of Mulholland, and that name's familiar to you. Mulholland Drive in Los Angeles was named after him. And it was a controversial issue even then. Farmers in the Owens Valley who effectively had that water drained away from their farms were angry enough about it that they actually blew up some of the aquifers with dynamite in the 1920s, and gunfire was heard across the valley as that project was constructed. But it became an essential part of the growth of Los Angeles. And after World War II, with a lot more growth, water was then taken from the Colorado River, which is the eastern border of the state. But there is about 240 miles of canals and pipework taking water from Lake Havasu, which is held back in the Colorado River by the Glen Canyon Dam. You can see there. That's one dam to the downstream of the Hoover Dam. But with a bunch of pump stations and canals, water is taken all the way to Los Angeles. And that alone wasn't enough. In the 1970s, more water was taken from Northern California, around San Francisco area, with 700 in California, around San Francisco area, with 700 miles of canals and pipelines bringing it down to the Los Angeles area. So a lot of imported water is brought into that system. But as I mentioned before, with drought, that Colorado River basin relies on the Rockies getting a lot of snow. And with increased populations in California, in Arizona, in Nevada, there's additional stress on that water supply. The Colorado River water is divided up between Arizona, Nevada, California, and Mexico, which is sitting at the very bottom of the Colorado River basin. And there are agreements which were signed between those states nearly 100 years ago, which divided up portions of water which in low water situations don't exist. And so California, although they do have first rights to that water, because when the negotiations were made, Nevada and Arizona were relatively small populations, they are working towards easing off some of the reliance on that particular water supply. And then when it comes to water in the Owens Valley and the local water supplies in California, the decreasing snowpack in the Sierra Nevada is also an issue. One of the things that is a common sight every year in California during the drought was the governor walking up to a particular spot in the Sierra Nevada and measuring the snowpack depth at the end of each winter to give people in California an understanding of what the drought impacts would be. And regular news reports of the snowpack will feature in news reports here in the West Coast and the western states of the US. Not dissimilar to the drought in Australia when we would get the dam levels. Well, here it's all about the snow levels. And so reuse has been in place in California, as I mentioned, since the 1960s, and regulations have been in place for non-potable reuse and potable reuse since about the 1970s, 1980s. In California, we refer to the Title 22 regulations, and it's a bit of a misnomer. Title 22 is in fact a broad suite of California regulations that cover anything to do with public health and public welfare. So you'll find a whole bunch of stuff there if you look it up online. But there are sections of Title 22 which speak to recycled water. And there are effectively 3 approved classes of recycled water in the United States right now. There is non-potable, and I won't go into the different subclasses of non-potable that there are, but then there are 2 indirect potable reuse water classes that are approved currently. There's groundwater replenishment and surface water augmentation. So treating water and putting it back into the aquifer, or treating water and putting it into surface water. As I mentioned before, there's a long history of indirect potable reuse in California. The picture there is of the Montebello Four-Bay Spreading Grounds, which is in eastern Los Angeles. These are just large ground spreading areas that take secondary effluent from one of the large wastewater treatment plants in the area. I think it's the Tillman treatment plant. Prior to the 1960s, stormwater was used for aquifer replenishment, and also imported water was used for aquifer replenishment. But since the 1960s, it's been treated effluent. And I should point out that California has some pretty ambitious recycled water goals. They're looking at, you can see on the graph there, in the parlance of California and the western states, we talk about acre-feet of water. For someone going up on metric, it's mind-boggling, but it's a number that came from the irrigation world, where, you know, an acre-foot is an acre of water covered by a foot of water. But a million acre-feet is roughly about 30 gigalitres, to put that into context. And I apologise, I am going to be probably talking in American units because I'm stuck with them. So case study I do want to talk about, and one that gets a lot of attention in potable reuse, is that of Orange County Water District. And Orange County is kind of wedged between southern Los Angeles and northern San Diego. It has about 2.5–3 million people, but very low rainfall. And groundwater basin there had been lowered from over-extraction since the days of irrigation and farming in the 1920s, and seawater intrusion has become an issue. In the 1970s, Orange County Water District were really leading-edge water managers and leading-edge technology people, in that they built a plant that contained reverse osmosis in order to produce a high-quality recycled water that had been desalinated to some extent in order to re-inject it back into the aquifer and push back against the seawater in what they call the seawater injection barrier. What's interesting about that is that this plant is about 15 million gallons a day. Sort of, you know, multiply that by 4, so 90 million litres a day, roughly, a little bit less than that. In the 1970s, that was bigger than any seawater desalination plant that had been built with RO at the time. If you look at the slightly blurry process flow diagram there, fortunately it's a little blurry, but what you can see is that it's two streams of water once it goes through pre-treatment, through the reverse osmosis, and then some goes through granular activated carbon and chlorination before blending and re-injection into the aquifer. By the 1990s, the California Department of Health granted that plant a permit to inject 100% recycled water without any blending. And what's important is that they've been doing this for a long time. I say 25 years of business as usual. I need to do my maths. It's more like 40 years at this point of business as usual of recycled water. And that's important because when it comes to indirect potable reuse for Southern California, it's been done for a long time. So folks are used to it and have good history of doing it. What I will point out at this point, though, is that Orange County 21 kind of set the precedent for reverse osmosis and potable water treatment. And even though one of the real drivers for using reverse osmosis was salt removal, to get the salt levels down for injecting into the aquifer, because it did such a good job of organic removal and of some of the chemicals of concern, in some ways it became the standard. And in some ways that's become a little bit of a shackle for potable reuse in the United States, because it's seen as the one and only way of doing it, when in fact there are other technologies that may be suitable. And I'll talk about some of those as we go. In between in the early 1990s, microfiltration as a technology in drinking water and in reuse became something that was a very effective pre-treatment to reverse osmosis, and something actually that was pioneered in Australia. And following some successful Australian projects using microfiltration ahead of reverse osmosis for reuse, Orange County spent a number of years piloting the same technology. And by 2008, built the upgrade to Water Factory 21, which they call the Groundwater Replenishment Scheme. And this is a project which produces more water, so with the water that they don't use for the seawater intrusion barrier, some more water is pumped up to Anaheim, right by Disneyland, where it is allowed to spread for aquifer recharge. One of the things that I'll point out here again is that Orange County spent a lot of time and effort on a public education campaign working on getting the public engaged with this process, and have had great success with the general public in public outreach, and are really a landmark for doing that. Again, groundwater replenishment scheme has the advanced treatment process, which we call the membrane-based approach, or sometimes you'll hear it called full advanced treatment here in the US. That's MF, RO, and UV advanced oxidation, which is a high dose of UV with an oxidant like hydrogen peroxide or chlorine. That is there to take up some trace organic material that was found persistent in California, nitrosamines or NDMA, and which is something that's formed in the wastewater treatment process to a degree, or formed in the advanced treatment process, and 1,4-dioxane, which is something that is well, not particularly common, but occurs in Southern California because it was used industrially in the 1950s and 1960s, and is persistent in the groundwater, and then ends up in the wastewater treatment and needs to be treated. And so the RO-based treatment process, or the advanced treatment process, is one that we see commonly for a number of treatment systems, particularly in California, also in Texas. One of the things that is important to sort of finish on here for California is that the energy consumption is important to look at. If you look along the x-axis there, OCWD, GW there, about midway where you can see the arrow pointing down, gives you a bit of an indication of the energy consumption. If we compare that to the chart to the right, the cost of pumping water across from the Colorado River and then treating it is another 50% again on top of the energy just to recycle the water that's there available in Orange County. And then if we look at State Water Project, where it's coming a lot further, more energy again, and then seawater desalination, which we have seen one desal plant built in California, significant energy consumption again. So potable reuse stacks up well. I mentioned before that in California, indirect potable reuse for groundwater and for surface water is now been adopted. It took a long time for them to adopt a final rule, but a final rule was adopted in 2014. Prior to that, each project was case by case. It needs, it's either disinfected tertiary with spring basins like Montebello Forebay, or advanced treatment with direct injection. One of the things that is important to point out is the rules and the requirements for removal of microorganisms. And one of the things that California has is a very strict level, and I'll get back to those numbers in a minute. One of the things that California has also been working on is an investigation into direct potable reuse. And in 2010, a Senate bill went through the California state government, which mandated a review of the feasibility of direct potable reuse. And an expert panel was set up to review that potential, and a number of research projects were funded through the Water Reuse Research Foundation, now part of the Water Environment Research Foundation, to support research in those areas. I'll get back to a couple of those projects in a moment. One of the things that is an interesting thing to note in California is a shift in public perception with respect to reuse. San Diego in the late 90s was looking at potable reuse for surface water augmentation as part of their water supply. That project was effectively mothballed or shelved, I should say, wasn't built because of a lot of public reaction. The famous toilet to tap phrase really had its genesis in San Diego. But with the drought and increased public outreach, there is now a revitalized project going ahead in San Diego, and in fact 30 MGD of plant is currently under design for surface water augmentation, so there's been a real turnaround. What I was going to talk about was the pathogen removal requirements for IPR and for DPR in California, and what the state's come up with. And just quickly, when we talk in this game, we talk about log removal. One log removal is a 90% removal. So 2 log removal, 99% removal, and so on. And so when California was looking at developing their removal requirements for direct potable reuse, they look at managing a 1 in 10,000 risk of infection per year. And with that risk, they've come up with these criteria of removal: virus removal of 12, log removal Cryptosporidium giardia removal of 10 log. And I should point out that is with a starting point of raw sewage. So between raw sewage and something that we drink, that's the minimum removal that we need to achieve. From a chemical standpoint, the state requires that drinking water levels are met, and in the United States, as many of you will know, we don't have guidelines, we have rules. So the EPA mandates a minimum water quality for the whole country, and then each state may have additional requirements on top of that. When it comes to reuse, California uses TOC, total organic carbon, as a broad surrogate for chemical removal and requires less than 0.5 milligram per litre in their treatment systems, and then has specific requirements for some of those emerging contaminants I talked about before. Some new technology approaches that California are looking at: membrane bioreactors on a large scale are being looked at very closely. The wastewater treatment plants on the coast in California are not specifically nutrient removal, they're only carbon removal. And so from a treatment perspective, in order to get to direct potable reuse, upgrades and improvements of those wastewater treatment plants are desirable. Membrane bioreactors are being looked at because we get part of the membrane, part of the virus removal, part of the microorganism removal barrier upstream. And so substantially large projects are considering that, and they're in the feasibility stage right now. I did want to talk about the water reuse research, or the Water Environment and Research Direct Potable Reuse Initiative. I've got the website listed at the bottom there, which I recommend you have a look at. About 30 projects or so that look into the technical aspects, public outreach aspects, operational aspects of direct potable reuse and its feasibility. A lot of good work there for indirect potable reuse and direct potable reuse in general. And I do want to point out that there was a significant Australian involvement, and continues to be, in a number of those projects. The use of critical control points, Project 1303, had its genesis really in a lot of the work that was done on the Western Corridor project in Queensland and in other projects there as well. Similarly, an operational framework project took a lot of work from work that had been done in Australia. So a lot of good connections there. Okay, I'm going to have to move a little bit quicker as I'm watching the time, but I do want to talk about Texas. And Texas is different. It's different in many ways from other states in the US. It does act as a bit of a standalone state. It did have a significant drought through the 2010s. It's now eased somewhat, as has California's, but it had some significant droughts that were towns and municipalities that literally ran out of water. One of those was the city of the town of Wichita Falls, not far, a couple of hours north of Dallas, and Big Spring, Texas, which is over in the oil areas to the western part of the state. And Texas, given that condition, moved towards allowing direct potable reuse on a case-by-case basis, and to date is really the only state in the United States that has done that. It essentially requires reverse osmosis for their treatment system, so goes with the full membrane treatment approach. Although they have done reuse using other types of treatment process, these were the ones that were allowed for direct potable reuse. And when we talk about direct potable reuse for these systems, they were emergency supplies. Wichita Falls had a treatment process that was indirect potable reuse that switched over to direct. And by direct, in these parts of the country, there are long raw water pipelines that feed some of these communities over some distance from reservoirs. So in the case of Big Spring, you can see the diagram there. The advanced treatment process basically added water into that raw water line, which was then treated at conventional treatment, drinking water treatment systems downstream. So upstream it was a membrane MFRO, advanced oxidation process, which then fed into a raw water pipeline. Each of these systems, though, was enabled under a permit waiver. So it's difficult to permit. There's no permitting for direct potable reuse in general. It needs to be a case-by-case basis. The Texas Water Development Board has developed a final report and a resource document that assists utilities in case they need to go ahead with permitting. That's worth looking up as well, from a good resource for reuse and indirect reuse as well. What one of the important differences is in the requirements for Texas is the microbial log removal requirements. You can see there in the table that it appears that the requirements for Texas are less stringent than California. Virus log removal is only 8, Giardia 6, Cryptosporidium 5.5. The difference, however, is that Texas begins their assessment of log removal downstream of a wastewater treatment plant. So they assess that risk based on secondary effluent, whereas California is basing that risk assuming that there's no wastewater treatment plant, that they're starting with raw sewage. So effectively, when it boils down to it, they're very similar. Quickly, Florida. Florida, as I mentioned before, is the biggest user of recycled water in terms of states in the country. Its rules define different classes of reuse. One of the things that's really driving up reuse in Florida is ocean outfall legislation, removing or reducing the amount of nutrient that is ending up off the coast and impacting coral reefs. So in a combination of growing population and those requirements, reuse is becoming a particularly interesting field. One of the other things that's important to point out is that Florida is a very, very flat state. There's not a lot of surface water that is captured and stored in that state, so it does use a lot of groundwater traditionally. A lot of work has been done here looking at non-RO type treatment processes. A study here done in the city of Hollywood in Florida, not to be confused with Hollywood in Los Angeles, used a combination of filtration, ion exchange, ozone, BAC and UV for aquifer recharge, rather than going through a reverse osmosis system. Important to point out that the water was recharged into the Floridan aquifer, which is an aquifer that is moderately saline and so requires treatment on the way out. So the system was operated in that fashion such that RO wasn't used twice in a sense. And from an energy standpoint, you can see here that using that treatment process had some specific benefits and energy savings. Now, an interesting state to sort of finish on here is the state of Virginia, which is, it's halfway up on the right-hand side. It's the state that nestles Washington, D.C., gets a lot of rain and has a lot of catchment, so it's kind of surprising that reuse might be considered in this area. Although reuse has been used for a number of years in Virginia, the Occoquan Reservoir has been recycling water indirectly for some years from their wastewater treatment plant through a somewhat advanced treatment system. But there is a focus in Virginia on groundwater, and there's a focus on the coastal plain. So Chesapeake Bay, which Washington, D.C. drains into, and a lot of Virginia and Maryland also drain into, has significant environmental impact issues, and there are drivers for nutrient reduction and nutrient removal into that catchment. There is also an issue with aquifer seawater intrusion, seawater levels rising, and subsidence because of aquifer over-extraction. There's a picture that you can see where Chesapeake Bay is there with respect to Virginia and the states surrounding it. So restoration of Chesapeake Bay is a big issue, impacting the groundwater resources, and depletion of groundwater is an issue. Seawater level rise is an issue. A lot of those areas around Chesapeake Bay are quite low lying, and sewer overflow, wet weather sewer overflow issues are also an impact for Virginia. The Hampton Roads Sanitation District in southeast Virginia, which is very, very close actually to some of the first settlements, first British settlements in North America, is a coastal community is quite vulnerable to sea level rise. It has seawater intrusion. It has a lot of focus on mitigating nutrient impacts to Chesapeake Bay, and so they're embarking on a $1 billion program in order to improve those conditions. And a project that's called SWIFT, the Sustainable Water Initiative for Tomorrow, is a project which takes effluent from their treatment system, goes through an advanced treatment system, and then provides clean water into the aquifer. And the utility here, Hampton Roads Sanitation District, is embarking on a 1 million gallon a day demonstration plant in order to demonstrate that technology. And one of the drivers here is nutrients, and basically with a combination of advanced wastewater treatment and then ultimately reuse, the utility is working further and further and further on reducing the nitrogen load into Chesapeake Bay. And ultimately, the red line at the bottom there is the projected total nitrogen load that will be able to be achieved once that full system will come online. And picture here just gives you an indication of the general trend in seawater rise around that area. It's going to be a significant issue around that part of the state. And the picture you can see here shows the aquifer compaction that's modelled. So that's basically compaction or subsidence is the other way of looking at that, taken from both historical data and also from some modelling data. And then on the right-hand side, if that reuse system and aquifer injection is employed, how that will be somewhat, will significantly mitigate it. And this process uses a non-RO membrane treatment system, so focusing on filtration, ozone BAC, GAC to take out all the organics, and various disinfection processes, so with a combination of filtration, ozone, which also acts as a disinfectant, UV and chlorine to manage pathogen removal requirements. And currently that city is building a 1 million gallon a day facility in order to provide both the technical answers and also get good public buy-in and visibility into ultimate treatment systems for that city. So important, and I bring this up because although we often think about reuse as being in the dry areas, even in some of the higher rainfall areas in the United States, potable reuse has seen some significant drivers. So as some concluding thoughts, potable reuse in the US is rapidly being seen as an option. And even though the droughts in the western part of the country have eased, there's been no let-up in the work that's going ahead towards new projects and new development of those systems. The regulations differ from state to state, and working as an engineer in the US, there's a lot of different regulations you need to be abreast of and navigating the waters of those regulations. In some cases, the regulations are lagging behind. I didn't talk about Arizona for time today, but I'm involved with supporting the Department of Environmental Quality here because they are looking at revising their regulations to adopt potable reuse and direct potable reuse as well. And there are multiple technologies that are used, and there are site-specific considerations. Different types of technologies are used for reuse in different areas of the country for different reasons. I think I've gone a little over time for questions. Hopefully I have some time for questions now, but I wanted to thank you all for your time, and thanks for the opportunity to have a chat with the folks back home.
Thanks so much, Troy. Really interesting presentation, as I'm sure our participants agree. As I mentioned at the beginning of the webinar, if you're able to type your questions into the text box in the bottom left-hand box there, Troy will be able to read them and answer them. So the first one there's from Aaron.
All right, let me make sure I'm looking in the right place. Aaron, okay, what kind of community education programs have they developed for introducing water reuse? It varies across the country, and some of the really good examples I think that have been that I could point to are in Southern California. Orange County has been doing it for a long time and has never really stopped their public outreach since they really built their first facility in the 1970s. They've engaged community groups, they've engaged, they have regular tours of the facility, they have a spot that they take school children through the facility all of the time, and they engage a lot with their local community. San Diego is something that's interesting because they've done it in a shorter period of time. San Diego kind of learnt their lesson, that they weren't doing enough good public outreach and community education programs when they charged ahead in the late 90s with their process, and they fell foul of politics and were not able to proceed. They kind of learned from that lesson and engaged with the public for a long period of time. The drought certainly helped, and I think it really gave people in California a good understanding of the kind of environment that they live in. Seawater desalination plant was built in San Diego as well. The other areas of the country, to finish San Diego, they've done a really good job of putting out good community information. They've got a great website that I'd recommend you go and look at. It's called the Pure Water. The Pure Water San Diego. It's really good. In Texas, the public outreach was also important when they were going to DPR. When you're in a significant drought, though, there's a lot of focus on the mine, so I think they were able to get ahead with it for that reason. Okay, let's see. I'll just go back through the questions here. The slide comparing costs of energy. Let me see if I can go back to that. This is a slide. You can find it actually, I think the Water Reuse Research Foundation or the Water Reuse Foundation also commonly shows. This one, I think, is the one you're talking about. I should sort of point out what some of the other things are here. That the recycled water on the far left-hand side is non-potable. So that's with less treatment. Groundwater is pretty common in California, so there's a lot of groundwater supplies. But if you want to get a copy of this, if you go to the Water Environment Research Foundation, I'm sure you'll be able to get one. So Bridget, the question on emerging contaminants, yes, there are concerns about emerging contaminants, and a lot of work has been done by the Water Environment and Research Foundation to try and address those particular questions. And I didn't, for space of time, I could have talked a lot more about some of that work today, but I didn't, just to try and give an overview. In general, there's been and continues to be a ton of work that's going on in the field looking at, number one, the likelihood of those contaminants getting into the treatment system at all. So a lot of work that goes into source water management and source water characterization. A lot of work looking at secondary and tertiary effluent from wastewater treatment plants because that's an easier matrix to do analysis in. And what's found from a lot of the water quality assessment and risk assessments that are done is that a lot of the contaminants that are of concern are actually lower than or less than the drinking water requirements even in the secondary effluent. For those that are continuing to emerge though and continuing to be found, there's a lot of work going on looking at bioassays, a lot of work looking at surrogates and indicator compounds, and then on top of all of that, from a treatment process reliability standpoint, a lot of work going into reliability of instruments, reliability of systems, and the critical control point project that my company was involved with, leveraging from a lot of work that had gone on in Australia, sort of takes it to the operational interface of how to manage some of those risks. So a ton of stuff there, Bridget, and I recommend that you hop on the Water Environment Research Foundation website and you can access some of that research work. Constantine, what would be your lessons learnt from the Western Corridor project to make it happen there in the future? I think that Western Corridor is a great example of having the right technology in the right place to do the right thing that probably just needed more time from a public outreach point of view and a public engagement and a public buy-in. The Western Corridor has done some great work in developing the systems and operational processes to really guarantee water quality safety and water quality and treatment reliability. So in some ways I think it's kind of dusting a lot of that work off and then comparing it to a lot of the work that has happened since and has worked in parallel in the United States and in other parts of the world on advancing research and advancing knowledge in potable reuse, and really kind of reflecting back and seeing that a lot of the things that the research is bearing out and all of the recommendations that are being borne out in California and other places is consistent with the way that Western Corridor went about developing their operational systems and processes and develop them. So I think there's a real opportunity there to almost see all of that good work come back to support that project. And given the greater number of jurisdictions in the US, how successful are collaborative efforts in implementing greater reuse, and what are the conditions that make collaboration viable? One of the most important elements of collaboration is the Water Reuse Foundation, which assists and becomes a forum for a number of the states to work together. One of the big things that as an engineer I'm always trying to make sure is happening is that regulators are talking to one another and regulators are learning from one another. Often as a consultant I go to lots of conferences and see lots of professionals and we begin to sort of hear the same message all the time, and we think that everybody is on board, but we need to remember that sometimes regulators from some states don't get to go to those conferences and maybe aren't as tuned in. So, kind of like bees taking pollen from flower to flower, I think that consulting engineers probably take knowledge and information from utility and regulator to regulator and make sure that we sort of pollinate that information across. But the Water Environment Research Foundation, a lot of research happens collaboratively, and it is encouraged to happen collaboratively. Projects are more successful if they engage more states. And one of the criticisms that's often made is that things here are a little too California focused. And so there is an effort to work with the other states and to look at what's occurring in the other states. Richard, is radioactivity a problem? Not particularly. It does need to be assessed, though, along with other water quality constituents and constituents of concern. Most of the radioactive compounds tend to be well removed if they exist at all. Radioactivity can be an issue in water supplies from groundwater. Particularly in eastern California, in Arizona, some of those groundwater supplies come out of the ground with uranium, vanadium. Just pick the lanthanide series up off the periodic table and you find it there. So there is work, actually a lot of it in the groundwater field in treatment. Although to be honest, most of the issues around radioactivity are waste disposal more so than actual treatment. Any work on stormwater flows in the treatment process? Yes, there is. There's a lot of work on looking at incorporating stormwater and a lot of work looking at blending of potable reuse in supplies. Again, I think probably the best place I could direct you to, again, is the Water Environment Research Foundation. Just sort of one thought on stormwater, and one of the challenges with stormwater is if you look at Los Angeles from the air, one of the things that you will immediately see is the great feats of civil engineering in the stormwater drains that crisscross the city. And they were built for flood mitigation in the times that there's significant snowmelt and high rainfall that could be damaging. But it comes in very short spurts and then it's gone. So it's all about capturing. Let's see. Aaron, you're from Arizona. I have to find out where exactly from. Given your perspective, what opportunities do you see for Australia to learn from the US or vice versa in progressing reuse initiatives? I think there's a lot to learn from each other, and I'm always keen to point out the role that Australia has played in a lot of the research and a lot of the technology development that has enabled potable reuse to go ahead. A case in point is microfiltration being used for reuse. The Orion plant that was built in the early 1990s at a power station, but using microfiltration ahead of RO, really saw that technology get good uptake into reuse, and it's particularly in the western part of the US, it's ubiquitous in terms of it being applied for reuse treatment. I think that there are a lot of commonalities between particularly the arid regions of the United States and say the west coast of Australia, where similar climatic conditions, similar water issues, similar water treatment goals, And look, I think it's encouraging that if you look at, if you did a literature search on the Water Reuse Research Foundation work that's going on, you'll see lots of, University of Melbourne, University of New South Wales, and so on. There's a lot of Australian collaboration that's going on. So I think that's a really good thing that should be continually fostered.
Wonderful.
Okay, I'm out of questions.
I think that might be the end of our questions. Oh, there we go. One more from Richard.
Oh, hang on, Richard. To what extent are renewable energy sources being used to power the plants? That's a good question. So we aren't seeing, I'm just going to pause and make sure I get my answer right here, but we aren't seeing necessarily a lot of renewable energy integrated into the plants themselves, but there are offsets that are used. Depending on where you are in the United States, there are more or less drivers for renewable energy. In Arizona, where I live, the power cost is relatively low. I'm sitting about 30 miles from I think it's the world's biggest nuclear power plant, so that's a relatively cheap source of energy, and so we have relatively low energy costs here. Having said that, there's a lot of sunshine and there's a lot of space, and so there are some solar-powered systems that are, there is solar power generation that's here in the state. California energy is more expensive, and so there is probably a bit more of a push for solar energy and wind energy that you'll see in that state. But it's similar, I think, what we saw in Australia, where it's a power that is built and then it offsets those supplies. I think given the oil price currently, perhaps given the regulatory appetite in the country at the moment, we might not be at a high tide mark for renewable energy, but it's watch the space.
Thanks so much for your presentation, Troy. I know that we all really appreciate your time. And just to let everybody know, this webinar has been recorded, so we will be able to distribute that to all attendees. Thank you again, Troy, for your time, and I look forward to many more webinars with you in the future.
Thanks very much, Kelly, and thanks very much, everybody. Have a great day. It's my time to knock off.
Thank you, everybody.